Starting now, we switch our viewpoint on electronics. So far, we've been studying electrostatics, wherein the charges are stationary, hence static. But things get more complicated and more interesting when charges are allowed to move. This is, by the way, I didn't write here, but this is electrodynamics, things able to move. Although we'll generally start talking mostly about circuits and then later into electrodynamics. Remember from before that a conductor allows charge to flow easily, whereas an insulator has charges that are mostly stuck in place. The quantum mechanics of why, for instance, metals allow charges to flow easily is obscure and, well, kind of interesting, but kind of weird, where in a metal, you have all the positive things, and of course, well, let's say in an insulator first, insulators, they're all basically surrounded by electrons, and the electrons are bound. Insulators actually don't have to be crystalline like this either, but whatever. In a metal, some of these electrons are actually in sort of this, what's called the electron sea, and they're shared among all the nuclei. And that is a result in part of the crystal format of metals. They're arranged in pretty well-defined crystals, which has this mathematical property that the electron the wave function repeats itself. And so the electron is sort of shared everywhere. And so it's pretty easy to move one of those electrons to somewhere else in the metal because in some sense it already partly exists there. You don't need to know that quantum mechanics for the AP test, but it's just interesting to know that there are some deeper explanations for why some things are conductors and some things are not. All right, imagine a capacitor. Remember, that's a pair of plates carrying opposite but equal charges. If we connect the plates with a metal wire, i.e. a conductor, we'll observe the charges on each plate will decrease. Eventually, they'll both be zero, and the capacitor will be discharged, meaning, obviously, no charge. Apparently, charge has moved along the wire from one plate to the other, and we call the flow of charge current. All right. Notice that it might be that charges move from both plates, that a negative charge moves this way, and a positive charge moves this way. But that actually isn't really necessary, because even if only the negative charges move, they will eventually cancel out. And so the plate will become zero. Even if we don't pull anything off the positive plate, the eventual charge will be zero as we add negatives, and those negatives coming from the excess negatives on the original plate. All right, we'll quantify current later. We'll give it numbers because this is physics, and physics is about numbers. But for the moment, let's focus on some phenomenological signals that current is flowing. How can we tell if there's current flowing? 1, a wire will get warmer. 2, if the wire is thin enough, it might begin to glow. This is how an incandescent light bulb works. Your textbook just says light bulb because it's sort of still written by old people who don't realize that a lot of light bulbs in life today are not incandescent, so they glow for other reasons. But your light bulb, the classic light bulb at home or a toaster oven, as the wires are thin, so as you try and push current through, they radiate heat and then eventually light. And also, if you bring the wire near a compass, a little magnetic thing tells you where north is, the compass will deflect. So that instead of being, if we have a compass needle pointing north that way, and then we bring it by the wire, it will look a little bit not north. It'll point, instead of pointing like that, it'll deflect by some amount. And that has to do actually with the magnetics, and we'll defer talking about that for quite some time, but it is a reliable indicator of current. And each of these effects gets more pronounced when the current is larger. So if you push more current through a wire, it gets warmer, it glows brighter, and it will deflect the needle even more. So this video gives some illustration of those kinds of things. This is a capacitor. It's not a parallel plate capacitor, I think. Maybe it was. And now we're going to discharge that capacitor. The way they know it warms the wire here is they're going to put it under thermal camera. And you can see as the current flows, it gets brighter and brighter. Then they got to set it back up. All right, in an incandescent bulb, there's a filament, which is a very thin thing, and when I connect it back up, it will make the filament so hot that it glows. They have to do this, of course, each time they're draining the capacitor while they do that. And then we get our current deflection there. The charges that actually move are called charge carriers. Naturally enough, we're really not that creative in physics when we name things. In metals, these are the electrons that are shared by all the nuclei in the metal, so-called conduction electrons. And we have a model here from your textbook where you have a lattice, basically, of ions, positive ions, nuclei, and possibly some electrons that are tightly bound. And then we have the conduction electrons, which are loosely bound and therefore can move throughout the metal. All right, they're not really bound to any particular ion, they're bound to the whole solid, and so they can move around. The metal as a whole is electrically neutral. All right, we're not talking about excess charge on a conductor, just where we can move the electrons. But introductory textbooks kind of make this accidental implicit mistake where they make you think that electrons are the only things that can be charge carriers. And that's because usually it's metals in circuits that we're caring about, and so we generally talk about conduction electrons. But if you have, for instance, a solution, an aqueous solution, it might be conductive. There might be positive and negative ions, and they can generally both move. So it doesn't have to be negatives that move, although in a metal, which is the most common situation, you will have just electrons. Another situation would be a plasma, which is a gas so hot that electrons have been stripped from the nuclei, they can't stay bound, and therefore both the electrons and their leftover nuclei are charge carriers. How do you create and sustain a current? Well, you apply an electric field, some external field. Somehow you generate an electric field and it causes stuff to flow through the wire. Think about a mechanical analogy. If you slide a book along a surface, the friction will reduce the kinetic energy and stop its motion unless you provide energy somehow, by, for instance, pushing it continually. You can make the book slide longer by polishing the surface and reducing the friction, and some surfaces are slick and allow easy movement while other surfaces are rough and resist it. The electrical equivalent of a slick surface would be a conductor, one that allows things to move easily. That of a rough surface is an insulator, and that of the push is the electric field. If the field is constant, each electron will on average move in the opposite direction, but only on average because they bounce off each other and off the positive nuclei. All right, we have them bouncing along, we have an electron moving along, and let's take, do we have one? Something like this, and it wants to, right, we have it moving randomly and it's curved by the electric field. Remember that for an electron, the force is opposite to the field. So it's dragged to the right, but then it bounces off this guy and starts more or less from rest and is accelerated to the right, but bounces off this guy and kind of does this little drunken walk all over the metal. Each collision scrambling the velocity of the electron. But there is a bias that tends to move them against the field. Why against? Again, because they're negative. The average velocity of an electron would be constant. All right, if we've averaged out how fast they're going on time, in general, in time, that speed wouldn't change. We call that its drift velocity. And while electrons move very quickly through a metal, the drift velocity turns out to be only a few centimeters per second. You might want to object that earlier in the class we said that the electric field inside a conductor is always zero. And we did, and it wasn't a lie, because in that case we were talking about electrostatics. And because of that, there couldn't be any motion of charges, so there couldn't be any field because that would have moved charges. But now we're allowing charges to move. We're not saying they have to be held in place, so the earlier reasoning fails. It's okay to have an electric field. You might remember that the separation of charges between, for instance, these two plates creates a potential difference, right? High potential, low potential. How do we know it's lower potential? Because a positive charge would like to move that way, right? Like to move from one to the other. Because there's a potential, there's also an electric field. So if we put a conductor here, there is an electric field threading through it. And so we have the positive charges will want to move along that field and down to the negative plate, and negative charges will want to move along that field and up to the positive plate. Remember that electrons move opposite the fields and therefore up potential gradients. In reality, remember, it's okay, perfectly fine if only one type of charge actually moves. All right, if we only have the electrons moving, they'll still reduce the excess charge here and also reduce the excess charge here. The potential is what creates the field, so we can think of that as the thing pushing the current. The analogy that's good to get back to, if you think of current as being analogous to fluid flow, then the potential is essentially the pressure. Right? It plays the role of the pressure, the thing pushing it forward. And as usual, things will want to flow from high pressure to low pressure. All right, let's think about this one. We have a parallel plate capacitor. It's been charged. We hook up a bulb with 2 wires. Whoops, bad writing. This is a bulb. Is arranged, conducted by ideal wires. And we want to say, where is the current greatest, at location A or location B? Or the same. Or maybe we need to know more. And here we come back to the charge can't be created or destroyed, right? We know that. So the bulb isn't generating or eating electrons. But it also shouldn't be growing electrons, right? It can't be gathering electrons. And so every electron that flows in must have an electron that flows out. And because it can't gather them up, they must flow at the same rate, which means that it has to be the same rate from there to there. Now you might object, but the bulb glows. It's got to be consuming something, right? It's got to be, where's the light coming from? And the answer is it's not consuming the electrons. It's just taking energy from them. And actually, since the electrons have an average velocity that's the same, it's really taking them from whatever is maintaining that potential difference. There's sort of an analogy your book uses, which I like. Imagine you put a turbine inside a water stream. As the water flows down, some of it catches the turbine and it gets swung around, giving us work, right? Doing whatever, running your power plant or whatever. But the water then moves on. And that basically once the flow has started, very quickly this becomes a constant flow as this spins at some rate so as to clear the water properly. The turbine, though, doesn't use up the water. It doesn't consume water. Some water flows through it, but then comes out again. Right? It does take energy from the stream. So if the stream is going to keep flowing at some constant rate, there has to be a source up here, some pressure pushing it, and it's whatever is producing that pressure that gives you the constant rate. Right? Likewise, if you want the current to keep flowing, there must be some potential difference that's maintained. This is why if you attach the capacitor to a bulb, the bulb will eventually grow dim and turn off because the flow of charge will eventually stop because you'll have equilibrated the 2 plates. We formalize this as something called the law of conservation of current, which really just says that anywhere there's current in a wire, it's the same value. Right? The current is the same at every point in a wire. We want to be careful here because we mean like if I have a wire, but we don't want to have a junction. We're going to talk about junctions later. Because of the junction, really we have sort of 3 wires here, not 1 wire, right? We'd have A, B, and C, and this doesn't imply that the current's the same in A, B, and C, only that at any point in A or any point in B or any point in C where there hasn't been a chance for divergence, basically, where any electron that comes along here has to eventually pass through every part of the wire, and so the current's going to be the same. But an electron that goes here could go up to this way, or it could go down here, and so the current can be different. All right, 2 identical bulbs are connected to a charged capacitor by ideal wires as shown. Which bulb glows the brightest? And I'm sure it will be no surprise at all. They will have the same brightness because the current in the wire has to be the same. The current here is the same, which means at this point the current's the same. It all enters the bulb. Nothing happens to it in the bulb, so it leaves. And so whatever the current was coming in, it left here. And then it's the same current that enters this bulb and leaves.